In this problem, we want to illustrate how we can go through this two-step process to get the electric field using the concept of potential, but for continuous charge distributions. So we know for a continuous charge distribution how to get the potential. It's integration of Ke dq over r. So we want to see how to use this to get the potential, and then once you know the potential, how to get the electric field using this relation. So the problem we're going to tackle is the problem of a ring. We've done this before in the chapter on electric field. So we want to solve the same problem using the concept of potential to see how you can get the same result with a different technique. So the ring exists in the YZ plane, and the x-axis is perpendicular to the ring, and the distance between the center of the ring, which is the origin of the coordinate system, and the point P is x. The radius of the ring is a, and the total charge of the ring is q. And we want to find really we want to find the electric field at point P. So the first step we want to find the electric field at point P. The first step is to get the potential. So first, what is the potential at point P? Well, if we take a small element of charge dq, the potential due to this element of charge dq at point P is Ke dq over r. It's as if it's a point charge. Now, if you want the potential due to the whole ring, what would you do? You would integrate over the whole ring. So we integrate K dq over r for the whole ring. Now, in this integration, is r constant or not? R is the distance between the element of charge and point P. If you think about it, r is just the square root of x squared plus a squared. Well, a is definitely a constant, and x is a constant for this particular problem because we're getting the potential at point P at a fixed distance from the origin. As you integrate over the ring, the distance x is the same, it doesn't change. So doing this integration, we take x squared plus a squared all square root outside of the integration. So you're left with integration of dq. What's integration of dq? You're basically adding all the charge of the ring. But we know what the total charge of the ring was. It's big Q. It just turns out to be big Q. So the potential then at point P is just Keq over square root of x squared plus a squared. Now notice how easy it is to get the potential, because we didn't have to worry about components of electric field and take an element on the top, an element on the bottom, and prove from symmetry that you only have an x component. All this stuff that we did when we got the electric field in the first time in the previous chapters, we don't have to do it. So it's very easy to get the potential. Now, what we know is the potential as a function of x. So that means we can't get, if you want to get the electric field, the only thing we can get actually is Ex. Because we need to know how the potential changes as a function of distance to get the electric field in a particular direction. We only know how the potential changes when you move in the x direction. So the only information you can get from this is Ex. So if you want to get Ex, how do you get Ex? By definition, it's minus dv by dx. So there's the minus, there's d by dx, and then I put here the potential. There's the Keq, and then 1 over of this is just x squared plus a squared to the minus half. Now, how do you get the derivative of this quantity with respect to x? Well, keep the minus as it is. Kq goes out. The derivative of the bracket is the exponent, which is minus half, times the bracket to the power minus 3 over 2, times the derivative of what's inside with respect to x, which is just 2x. So you can see clearly that the 2 will cancel with the 2, the minus will cancel with the minus, and you get the final answer is that the electric field, the x component of the electric field, is Keqx over x squared plus a squared to the 3 over 2. If you go back to the notes that we did before in the chapter on electric field, you'll find this answer is exactly the same answer as we got before. So we're now learning how to get the electric field in an indirect way by first calculating the potential and then getting the electric field from the potential by a simple differentiation.